All right. Let's see here. We're only missing two. All right. Good job. Majority of the class showed up Friday before spring break. I applaud you. I'm willing to give you some imaginary points for that. Mm-hmm. All right. The last thing I want to talk about when we come back from spring break, I'm going to we're going to do data processing with Python scripts. So we'll write some like that script I wrote to do the average, right? It's a fairly handy thing to have, especially if you're building utilities that work on the command line. So we're going to, learn how to build scripts to take the average, maybe write one that does the standard errors so that you calculate the uncertainty in a data set, some histogramming, stuff like that. So the last thing I wanted to talk about is Gnuplot tricks. So things that we can do with Gnuplot now that we know how to use pipes. So pipes do one thing. They take the standard output of a command, they send it to the standard input of another command. Any command that reads the standard input can then have its input sent to it from a pipe. Gnuplot reads commands from the keyboard, which means it's reading from standard input. So we can pipe commands to Gnuplot's standard input. So an example would be if I echoed the string plot sine of x. Well, that's a Gnuplot command. If I pipe that to Gnuplot, Gnuplot will run that command. Now, one thing I'll notice is that if I see a flash at all, the window doesn't stay open because Gnuplot immediately closes after it executes that command. If I want it to leave the window open, I have to give Gnuplot an option persist. So tac persist will leave that window open. I can also send the data that I want to plot to Gnuplot through the standard input, but that's a little bit trickier, and we'll see how that works. And then I can even, this is crazy, Gnuplot supports pipelines in the plot command. If I give a file name that starts with this caret here, then instead of treating that as a file, Gnuplot will run the stuff that follows that and then take the output and plot whatever the result is. So we'll see how to do all three of those. All right, Gnuplot scripts. Got a sandbox for today. Going to want to download the sandbox, open it up. Just so Derek doesn't have to email me asking, it is not the same as it was last time. There is extra data in the sandbox this time. All right, so I'm in the sandbox directory. Recap how we use Gnuplot. So plot sine of x will plot the sine function. Oh, good thing I did that. I'm going to exit. If I echo commands to Gnuplot, Gnuplot will run those commands. So this is just saying plot sine of x, and I'm going to send that to the standard input of Gnuplot, which is where Gnuplot reads commands. And in this case, I don't see anything at all happen. It almost looks as if it doesn't work. What happened was Gnuplot ran the command and then immediately closed. And sometimes that happens even before you can see a window pop up. And on some cases, you'll see a window flash. So if you want that window to stay open, you need to use the persist option. So if I give Gnuplot the tac-h option, most commands support tac-h, which is help output. I can see that there's a persist option. There really isn't any description of what it does, but basically what it means is the window that is created will persist after Gnuplot closes. So I send this standard output of the echo command to the standard input of Gnuplot, and I use the persist option. And now I get a window that pops up. Gnuplot closes immediately, but this window is still open, which means this window is no longer interactive. Yes, Patrick?
It's like forking the process, so it shows up since you can type in another completely.
What's that?
Never mind.
No, what was the question?
Is it like forking the process? You can enter another command immediately afterwards, since you get your prompt back.
You mean is the persist option doing that? Yeah, I don't know. I don't know what it's doing. Let's see if Gnuplot's still running. So this will print out a list of all processes. Actually, what do I not have PS? There we go. There's a list of all processes. Let's look for Gnuplot. Looks like Gnuplot X11 is still open. So yeah, it must be forking it and still running it. So if I run another command, I will get another window, right? I need to explicitly close this window if I wanted to. So let's look at an example of plotting data. So I have some echo commands here. All I'm doing is just getting some data put into a file. So I'm going to echo 1 space 1 to data.txt. I'm going to echo another line to it. I'm going to append. So I'm basically just trying to create a little text file that has some data in it that I can run through Gnuplot. So I've got 3 lines in that data file now. If I look at those lines, all right, this is the stuff that I just sent to it from the echo command. All right, now let's plot that data file. I get a new window that pops up, right? This window I have to explicitly close if I don't want this up anymore. So I get a new window. It's a little bit hard to see, right? It says that it's plotting data.txt. There's one right here. The problem is that the auto scale has got all 3 points in the corners or on the extremes of this graph. I'm going to plot this with lines so I can actually see these data points connected together. And there we go. So I've got the first one, the second one, and the third one. Now, Gnuplot also supports reading the data that it's going to plot from the standard input. And I've mentioned this in previous classes. The commands that take file names and or standard input, most of them interpret the special file name, which is just a single dash, as standard input. So the cat command, for example, I could take the output of or the contents of a file and standard input and concatenate those together if I use the tac option or just the tac for the file name. Gnuplot does the same thing. So if I plot a file named just tac, it will read data from the standard input. The problem is I can't read data from standard input at the same time that I'm reading commands from standard input. So this is trying to read a command from standard input. When I give it this tac option for the file name to read from standard input, that's being used to interpret commands. So I can't get it done that way. What I can do, though, is if I look at the help from Gnuplot again, Gnuplot takes an option TAC-E, and TAC-E allows me to specify a set of commands that I want Gnuplots to run before it starts processing standard input. So, for example, if I put plot sine of x in the TAC-E option instead, it works exactly as it did before. That plot sine x gets ran right after Gnuplot runs. That is now getting commands into Gnuplot without using the standard input. So I can use the standard input for data. I'm going to tell Gnuplot that I want it to plot data from standard input. First thing, when I hit enter, I see it almost looks as if it's hung, right? Like it's not doing anything. What is it doing here? It's waiting for input, right? So it's reading standard input until it reaches an end of file character. So if I just start typing in some input for it, and then I do Control D for end of file, as soon as it gets the end of file character, it takes whatever I typed in, gives me standard input. Now I don't have to type in this stuff. This wouldn't be a very useful example for Gnuplot. But if I have data in a file, I can pipe it to this command and then get that to plot, which is a nice quick way of, one, if you want to control Gnuplot from a bash script to create a file or to create a plot, or if you want to, like a script that will just quickly plot a bunch of data points that you put on standard input so that you can just see what it looks like, right? Just a quick script to say, hey, I've generated a set of data points now, plot those so I can see what they look like. If I need to give more than one command, you can give more than one commands to Gnuplot on the same line. but you have to use a semicolon to separate the commands. So here I'm going to set grid, and then I'm going to plot from standard input, and I'm going to give the lines points option. So it's going to plot it with lines connecting the points. It's waiting for standard input now. Type in some standard input. Give it the end of line character. Now I have a plot with the data points connected, and there's a grid on it. Right, so you can see it's different than it was before. This is more likely what I would have. I've got a file that contains the data that I want to plot. I can pipe that to Gnuplot. I want it to read the data from standard input, not the commands from standard input. So I give the commands to Gnuplot through the TAC-E option. I tell it to plot the dash file, which means read from standard input and plot that. So this is now reading out of that file that I'd created earlier. All right, so I've got some examples. These are the same types of data files that we've looked at previously. I've got comma separated, space separated, tab separated files that have some data in them. If I look at the data in the files, right, this is a time and a position. So these are, you know, maybe some sort of measurement of an object that's moving, measuring its position as a function of time. I'm going to open up Gnuplot. I'm going to plot some of this data. So space separated data, not a problem at all, right? We know how to plot that. If I plot space separated data, it looks like this. So I've got time and position. Looks like it's maybe accelerating a little bit because it doesn't look like it's a straight line. Looks like it might be sort of quadratic. Tab separated, also not a problem. Tab separated data will be treated the same way as space separated data. These are different data files, so I have different data in there, but Gnuplot doesn't have any problem with that. It doesn't have a problem with multiple spaces or multiple tabs separating the data file, like the cut command did, for example. So anything that's separated by a space will be treated as a separate data point. All of that's fine. The problem is if I want to plot data that's in a comma separated values file. So now I've got data lines or lines that have the data points separated by commas. If I try to plot that in Gnuplot, I get something that plots, but it's clearly not right. It's just plotting a straight line. Now, Gnuplot does have support for changing the data file separator. So I can give a comma as the thing that separates my data points. The way that I do that is I use the set command, data file separator option. So I'm setting for data files, the separator should be a comma. Now I try to plot that comma separated values file and it works as expected. But I can't plot space separated files now. So I'm gonna have the same problem if I try to plot a file that is space separated. It's just a straight line. If I want to set the separator back to white space, I use the set command again. But instead of giving it the character that I want to use, like I could tell it to only use a single space or to only use a tab, but white space will allow it to use any white space characters, tabs, spaces, and combinations of those. So I set that back to white space. Now I can plot my space separated text file again. But what if I wanted to plot them both together? All right, one of them is going to be parsed correctly and one of them is not going to be parsed correctly. So I have a couple of options. One is to create another file. So go onto the command line and create a space separated version of that comma separated text file, which we saw how to do in the previous class period, right? You can use sed to replace all commas with spaces. But I can actually do that conversion directly in Gnuplot because Gnuplot accepts a syntax where if I use this less than sign, then the string here is not treated as a file name, but as a command. And Gnuplot will take the commands, run them on the command line, And whatever the standard output of that set of commands is, it will treat that as the data to plot. So if I just cat the space separated text file, then I should just see the data in that file plotted. It's exactly what I get, right? Get the same thing as I had before. I'm going to put lines points on this. Bless you. And now I'm going to use this feature to convert all commas to spaces directly in Gnuplot using a pipe. So I'm going to cat the comma separated file. Bless you. I'm going to send that output to sed. I'm going to tell sed to replace all commas with spaces globally, meaning do it for all commas on the line. And then I've got with line points just so that we can see the lines, the data points connected together. And that works. My space or my data file separator is still a space. Yes.
So what if you forgot your G option on that and it only replaced the first comma, but you're graphing the first two columns in Gnuplot? What happens when it reaches that comma? What does Gnuplot do?
The next comma? I don't know. I assume that it sort of chokes on it, says, I don't know how to interpret this. Either that or ignores everything after it. For these files, there's only two lines, so I don't need that tag G or that G option. 2 columns, I guess I should say. So now I can plot the space separated file with lines points. LP, by the way, is an abbreviation for lines points. And I can plot the comma separated file on the same graph by using a pipeline in the Gnuplot file name argument. And there's my 2 data sets. So I've used this in various ways before. I've had times where I'll have a Gnuplot script that I'm going to use to plot data that is actually generated by some computer program that I'm writing, write a little C++ program to generate some data. So you can have a Gnuplot script that runs your program. As long as your program prints all of its data to the screen, it'll run the program and then plot it as soon as it gets done. Like what you've got going on, Tyler?
Getting that data on line 1 of file space separate.
That usually means that you've got a string in there that is not being interpreted as a, so run head on that. Is there a pound sign at the beginning? What's that?
I was saying that pound sign question.
Star exclamation point. I feel like now I'm gonna have that stuff in my head. Kevin Fowler.
So for that one script that I have, I don't have to make a temporary file and graph that file. I can just.
You can send it straight to Gnuplot. Did you get it figured out, Patrick? You want me to come around to the front side of that monitor? He actually comes around here. We saw him at Stockton Rodeo, yeah.
When was that?
It's been a while, probably before I started having kids. So 3 or 4 years ago.
So it's supposed to start off with the pound sign.
The header?
Yes.
The data files that I have in today's sandbox do. If it doesn't have a pound sign, Gnuplot won't ignore it and it'll choke on it.
Oh, okay. This one too.
Did you get today's current sandbox?
Yep.
You're telling me that
Today's
if
the
I,
17th, right?
Yep.
Yeah. I didn't modify it at all.
so you're saying if I download it right now, untar it, I'm going to find a file.
That was my computer's reason.
So it does not have a pound sign in for the header.
Mine's great.
Okay.
All right. I'm going to exit this. I want to show you another little trick. Not quite, I mean, we're going to use some pipes, but this is a nice little feature of Gnuplot. So I'm going to go in the sandbox directory, there's a directory called data, and inside there is a directory called electron scattering. So I've got some data files in there. There's a file called time of flight detections. And this file basically contains, I mean, it's of course fictional data, but the idea is that this is data that like Jack or Kayvon would collect in their apparatus. And they've got some electrons that are flying through their apparatus, and they're calculating or measuring time of flight at given positions. Now the electrons all have some, slightly different momentums, so they're moving at slightly different speeds, which means the time of flight from the beginning to position 1 varies a little bit each time. Time of flight from the beginning to position 2 varies a little bit, but on average, you can calculate what the time of flight would be. So that's what these are. So this first column is how long did it take to reach position 1? The second column is how long did it take to reach position 2? I don't know if what the feasibility of actually taking these measurements are, but it's just a nice way of giving us some data to visualize. All right, so if I open up Gnuplot and just see what the data in this file looks like, I'm going to plot time of flight. Now in this case, I'm not going to plot the first column versus the second, or the second column versus the first column. Each column is a separate data set. And if you tell Gnuplot to just use one column of data, or if your file only contains one column of data, then it will plot that data versus the line number. So this is a way for you to just see all of the data points on a graph. And the x-axis here is going to be the line number. So the first line would be this one back here. All right, so the first number in the file is probably around 210.5. Is that what that was? Yep, 210.5. So that's what we're getting here. You can see that there's sort of, it's scattered, but the range here is from 175 to 220. So they appear to be scattered about some average. So I'm going to plot the first column and the second column. So position 1, position 2. Now I can clearly see that position 1 and position 2 are numbers that are scattered, but they're not completely random. They're scattered about some average. So that's the data set that I've got. Position 1, 2, 3, 4, and 5 are progressively farther away. If I look at position 1 and 5, those time of flights are separated by a greater amount. All right. So let's do a little bit of processing of this data. One thing that I could do is, without opening up Gnuplot, I could plot column 1 by using Gauck to extract column 1 first. If I just plot a data set that has one column, Gnuplot will automatically plot it versus the line number. So all I'm doing here is get this time of flight data to the command line using cat, run that through Gauck, pull out just the first column, then send that column of data to Gnuplot. I'm telling Gnuplot to execute the command plot with dash for the file name, so it will read from standard input, and I'm giving it the persist option so that it'll leave the window open. Make this a little bit bigger. And this is the same graph that we had when we opened up Gnuplot. All right, so all of this stuff all of the data here is randomly distributed about some average. So what I'm going to do now is I'm going to plot the data sorted. So I run it through Gawk again to pull out the first column, and then I run it through sort, which is going to sort it ascendingly. So now I should get all of the low values first in my graph and all of the high values last in my graph. And I have foobarred this. There we go. So this is the same set of data. This one looks completely random, right? It's bouncing around some middle point. And then if I sort it, I can actually look at this and see which values are more common than other values, right? And so here in the middle, where if this was a horizontal line, it would mean that there were a bunch of numbers that were all the exact same. But it's not quite horizontal, but it's definitely not as steep as the stuff over here. So over here, there's only a few numbers that are down here by 175. I get up into this middle portion of the region, there's quite a few that are in between 195 and 205. And then I get up to the top, and there's only a few numbers that are between 210 and 215. So this is just a way to look at the data to try to get an understanding of what the data set looks like. Yes, Tyler?
What if we wanted to fit a line that would we say fit MX plus B to standard input via MB and then plot that?
I think so, yep. All right, I'm going to open up Gnuplot again. Now this type of data, where I have stuff that's scattered, but it's not scattered, well, even if it is scattered uniformly. This is the type of stuff that is very common to create histogram plots of. And a histogram plot would be, how many of these data points are 200? How many of them are 205? How many of them are 210? Let me plot the count as a function of the value so that I can get an idea of what the distribution of numbers looks like. And there's a nice little Gnuplot recipe, and I didn't come up with this. I ended up stumbling upon this at one of the, just on some forum. There's a nice recipe that allows you to basically calculate the histogram directly in Gnuplot and then plot it. So this is what the output of that looks like. So now you can see that around 200, this is the count. This is how many points are around 200. This is how many points are around 175. What's actually happening is this. So I've got my time of flight file, and then I'm telling it to use for its X and Y columns, something that I'm calculating. For the first column, I'm doing 2 times floor of the first column divided by 2. Now what that's basically doing is, it is saying, take the first column, divide it by 2, and then round down. Don't use the decimal part. So this is turning it into, if the number is 1, this will get turned into 0. If the number is 3, it'll get turned into 1. So I'm basically binning up all of the numbers. Numbers that are between 200 and 202 are all going to be counted as 200. And then I can count how many occurrences of that number exist. So all numbers between 200 and 202 get turned into 200, and then I can count how many of those there are. And that's what this second column is. The second column is just printing out a 1 so that there's a number associated with the y-axis. If I just plot that, it looks like this. So here are the values that are in my data file. These dots here, right? These are separated by 2. It's 178, 180, 182. That's what this first part here is doing, that floor function. They're all plotted on top of each other, so I can't see it. But if I looked right here, there's probably 5 or 6 data points that are actually right on top of each other. And so if I don't do the second piece of this, which is smooth frequency or smooth freak, then it just plots them all on top of each other. What this smooth argument does is it says actually plot the number of data points that have this value. So it's going to count and plot the count versus the actual numerical value. The other nice option that you'll often want to do with this one is, so I'm going to do smooth frequency so that it'll plot the number of occurrences versus the number instead of just one versus the number. And then I'm going to do with boxes. So with lines, we'll draw lines between points. With lines points, we'll draw points for every point and connect them with lines. With boxes, we'll draw boxes for the points. So here I've created a histogram of the data, which for some reason turns out to be a little more painful than it should be. As common as this is, as it is to need to do this, there aren't any tools that really do this very, very automatically. But this is a nice little recipe in Gnuplot that will allow you to do this. Yes, Tyler?
If you didn't put 4 and didn't include the dot on the 2 of your using command, would it just do integer division and automatic?
If $1, if the number in the first column is an integer, it would.
Okay.
But if it's a float, then it'll get interpreted as floating arithmetic.
Okay. Even if you're dividing by an integer.
Mm-hmm.
Okay.
Yeah, if either the numerator or denominator are not an integer, then it will do floating point. Smooth with the frequency and then put the boxes on. So from this, we can basically see that the majority of time of flights that are measured are around 200. Some of them are a little bit longer. So there's a couple of them over here that were longer. There's a couple of them over here that were shorter. But for the most part, the time of flight is around 200. This is with the boxes. Now, if I wanted to change the bin width here, so right now these bin widths are 200, or excuse me, 2. If I wanted to change the bin width, I change this number that I'm dividing by and this number that I'm multiplying by. So now instead of counting everything between 200 and 2010, 200 and 202 as the same, I'm going to count stuff between 200 and 220 as the same. It makes your bins wider, basically smooths out, probably smooths out the distribution. This apparently makes it very smooth, right? There's only one big one here, a big one here, and a big one down here. So this is something that you'll, if you're trying to histogram data, sometimes you have to adjust that bin size to get it to look good. One thing that I can do is, like this function, if I'm going to use this over and over and over again, I can just create a function that contains that and then use that for my column transformation. What did I do here? What is this, Patrick? Oh, okay. Here's what here I ran the command without the smoothing. But instead of putting a 1 in for the Y column, I just put the X column value in. So you can see that this is how the mapping is happening, right? Everything between probably 190 and what is this? This is 180. So this probably goes from 170 to 190 is all getting turned into 180. And then these are all the points that this would be the count that represents the height of that function. So I can use variables to make this a little bit cleaner, right? So instead of multiplying by 20 and dividing by 20, I could set a variable called width to equal to 2, and then I could do that calculation. So that it would be very simple to change the width. All I'd have to do is change the value of that variable and then rerun it. So I can use width here instead of explicitly putting the number in. But if I'm going to do that, I might as well just define a function that does that calculation. So f of x I defined to be this binning calculation. This is going to turn a number into some other number that is within a bin. So it's going to turn 205 into 200, 206 into 200, 207 into 200, and then I'll end up with a bunch of numbers that get mapped to the same number so that I can count the frequency in which that occurs. And so if I use a function here for one, it makes the plot command a little bit cleaner. But then if I want to plot multiple, if I want to use this in multiple data sets, it's easy to repeat over and over again, right? So this is the first column, this is position 1 data. I'm using the function to generate the binning so that I can plot that with a smoothing option for frequency. And then I'm doing the exact same thing, except I'm going to do it for column 5 now instead. And I'm going to plot these together. So what I should see are basically 2 distributions, one around 200 and one around whatever that column 5 looked like it was lined up around. And there it is right there. Let me do the same thing. I'm going to add the boxes. Oh, no. Let me add the boxes to that plot. $17. Where was that? In the data?
Yes.
2017. Man, we got a lot of these. What am I? What's the problem? Oh yeah. Oh, I know what it is. I haven't downloaded the latest. Let me go into here. Amateurs. Electron scattering. Okay. So let's do with boxes here. And let's do with boxes here. Oh, my function f hasn't been defined. It's going to complain about width. There we go. So I see a couple of things. One, this one's more narrow. This is distributed around 200, and it's fairly narrow. This one's much wider, but it's distributed around 1,000. So this is just a real quick way to generate histogram plots of data, which is very common if you have something that's based on some sort of random sampling. All right. One thing that I just want to explain what this is, so that, because I'm going to probably have a homework problem that does this. I was actually using the stuff that we were just doing earlier today. This morning I was running a simulation that was producing these data files, and then I wanted to plot something in the data file versus something that was actually in the data file name. I wanted to generate this plot. And so what I did was I wrote a little command line pipeline that extracted the information that I want. So if you go into the data directory, there should be a directory called retinal spot size. And it contains several data files that was generated by a simulation. And what this simulation does is it just calculates the distribution of energy on the retina from a laser exposure. So it's like, okay, well, if I looked into a laser, how much energy would make it to the retina? It's based off of that data set that we looked at in the previous 2 classes. Transmission is a function of wavelength. So a green laser is going to have more light that gets to the retina than a red laser is, assuming that the transmission is greater. And so the graph right here was created by plotting the retinal beam diameter versus the wavelength in nanometers. And the retinal beam diameter is contained in the file, and the wavelength is contained in the file name. And so what I did was extracted the wavelength and the beam diameter from the file and the file name, and then sent that to a file that I could plot using a Gnuplot. So what this shows is the retinal spot size. So if you look at a laser, how big is the spot on the retina going to be? It turns out that, the reason that a prism works is because the refractive index of glass is not constant with wavelength. The refractive index for water is not constant with wavelength. And so what you see is that your eye will focus different colors to different places. And this ends up being the effect of that, what's called chromatic aberration. So 400 nanometer light gets focused to a spot that is this big on the retina. I think this is micro, or this might be centa. I think that my units here are wrong, because this is going to be like 12 micrometers. If I start going to longer wavelengths into the green light gets focused to a smaller spot. And then if I go to longer wavelengths in the red light gets focused to a larger spot again. And that's what this graph was created on. So let's look at the data files and see what I'm talking about. Let's see here, let's go to 13. There we go. All right, so it looks something like this. You should see a bunch of files that look like this. So for example, for 800 nanometers, I've got the irradiance on the retina due to the ballistic photons, the scattered photons, and the total. Details of that are unimportant. Let's just look at this ballistic file. So if I open up 800 nanometers ballistic, no wait, ER ballistic. At the top, I have some header information. I have prefixed this with the pound sign so that this file itself could actually be plotted in Gnuplot. And the thing that we're interested in is this line right here. Both of these should be the same, and I didn't actually try to distinguish between the two. So I just extracted this line and this line. That is the beam diameter at the retina. The wavelength is not in this file. The wavelength is in the file name. So what I did was I got the wavelength from the file name and the beam diameter from the file itself, generated a column of wavelengths and beam diameters, and then I was able to plot that using Gnuplot. So for example, if I grep for, let's see here, W equals in all of these files, well, now I've got standard output that's got something that is the wavelength and is the beam diameter I'm trying to plot. From there, I can construct a pipeline that gets this turned into a number and another number. I only want to use the ballistic files in this case. All right, that's all I got for today. Any questions? Nope.